Yeah, I'm Michael. I'm a French student, French Vidais. And and I'm a graduate university. I'm in my second year. So I'm going to talk about some work I'm doing with Kevin Buzzard. So there's going to be a lot of talking about FOP. I will start with some archaeology just to explain what this theorem is about. It's a theorem by Deligne. So I have to talk about FLT, but of course Kevin will do it a little bit later. And then I'm going to talk about the theorem itself. Yeah, so what is FLT? It's a theorem that states that there are no three positive integers A, B, and C that satisfy the equation A to the n plus B to the n is equal to C to the n for any value greater than 2, if n2 is obviously the Pythagorean theorem. It was first proposed by Pierre de Fermat at 1637 in the margin of a copy of proof in Arithmetica. And he claimed that the proof was too large to fit in the margin. The claim was discovered by his son. It was believed that Fermat did not have a correct proof. And in 1994, 350 years later, Andrew Wells announced the proof, but it had a gap, but he fixed it a year later with Taylor. And this quest to prove FLT spurred the development of areas in number theory and algebraic geometry. So that's supposed to be important. What's the motivation? Well, Frege maintains a list over 100 theorems of formalizers. 99 have been formalized. The last theorem is actually Fermat's last theorem on the list. And
so it's Frege's last theorem.
And there's we care about it's a technical achievement because it's valid, like the proof is correct, but what we want is to drive the development of MathLib, which is a complicated mathematics library. I'm going to talk about it a bit later. So we can use all this mathematics and we can identify weaknesses in proving the technology, and you can also, if you have all this material formalized, you can use it for modern research, which is actual motivation. It's important to mention that these theorems by Wells and others are like a special case of the two-dimensional case of the language philosophy. There's going to be a seminar like about formalizing language stuff. So recent news. In 2023, Kevin Buzzard received a research grant to begin working towards a formal proof for Fermat's last theorem in Lean. This grant bought out his teaching and administration for 5 years, and he mentioned he will be working on a more modern version of the proof after discussion with Taylor, and it involves less analysis. So, a non-exhaustive list of ingredients. So we need 358 years, around 350 years of mathematical knowledge encoded and refactored. And they all use classical mathematics, as far as we know. Okay? Yeah, I get this a lot. And these are the ingredients that we want, some of the ingredients, and these are the people that have been working on these things, of course it's non-exhaustive. And then what you want to do, you want to prove some very deep theorems about some of these objects using the rest of these objects. Okay, so you have this complexity, and then you get a complete formalization of Fermat's last theorem. So let's go through the proof. That's the informal statement. And we have a flow diagram actually. What do we want? Well, the proof is by contradiction. So you assume that there is a solution, a non-trivial solution. And then what we do is we define what we call an elliptic curve. From there we construct a Galois representation. From the Galois representation we construct a modular form, or we say that there's a modular form associated to this Galois representation. And then we get a contradiction showing that such a modular form does not exist. So I don't want to blind you with science, I don't want you to talk too much about the maths. I'm going to show you how these objects look like. So now, okay, let's assume that there is a non-trivial solution. We can build an elliptic curve using the work of Helgoy and others from the 60s. And elliptic curves are like curves of this form. And there's some pictures how they look like. and then we can construct an irreducible Galois representation. So now we can jump from hard algebraic geometry to algebra. And for that we need a very profound theorem by Mazur from the 70s that involves a lot of advanced algebraic geometry. And it seems that all proofs need this, so even the modern one. From there, we want to construct a modular form, and we need some very hard analysis for that. So the new proof that Ken's claim you need less analysis, which is good. So what are modular forms? You have the complex upper half plane. These are functions from there to the complex numbers, and they look just like that. Well, the easiest way to view them is like your formal power series of this form. Okay, so it's like these with complex variables. And that's how they look like, and in a more interesting way. You have this fractal kind of like structure.
Can you generate those images from Lean?
Do we? Can we?
Sure, why not? It's a programming language.
That's one project for these.
Okay. 3D pictures.
Definitely able to make pretty pictures of the stuff. Yeah.
For now, you can find it here. There's a reference.
Okay. Verified 3D pictures.
Right, and then once we get this modular form, we can just apply all these deep results by Wiles and others, and we get a contradiction. We're going to get essentially a modular form with some properties that does not exist. Right, so how about the Deligne theorem? Well, this is Zina project. This is a blog Kevin. So she proposed like a few challenges. Well, first he said the challenge, we have this, she talks about Frey, right? So he says there's 100 theorems to be formalized. This is 2020, right? So 95 of them were done. And FLT is just silly. We need new challenges. Here are 10 off the top of my head, right?
Okay.
Yeah.
I read like Riemann hypothesis. I thought, well, that's kind of will be hard to prove, right?
Well, I mean, some people will complain there are no projects.
I didn't read the.
Yeah, so we want to test the limits of current proof assistance, and the idea is like, okay, can we have a prover that can do all 10? Some of them were done already, like Spirit Adventure was done by Patrick Massot, I think. These other things have also been formalized, some of them. My challenge, like what this talk is about, is the sixth one. It's like 6 million miles away from any theorem prover. But it's just a statement, okay? It's about stating this theorem. It's about formalizing the whole thing. So we need a lot of mathematical areas there are a lot of mathematical areas that are involved in the proof, and of course Deligne is also just like an example of the theorems that are involved in the proof for FLT. So what you have, well, it goes the other way, right? So what you have is that you have a modular form, and you want to construct a Galois representation with some properties. So in the proof, you have a Galois representation, you want to construct a modular form, but now in the Deligne theorem it goes the other way, and it's generalization of this K, K equals 2, which was proven by Eichler and Shimura, and that's the component that Wiles used in this proof. So how do you formalize a statement? Well, you formalize all the definitions that occur in the statement. And actually, these objects are very important for FLT in general. So how do you do that? How do you start? Well, the approach is top-down. It's not like you have a textbook and you start formalizing everything, incrementally. You create a roadmap first, and formal proof sketch is an idea. I think it's been around for a long time, but like Frey talked about it like for 20 years ago in a type seminar. What you do is like you omit details of proofs, not definitions. Definitions you need them, at least for in our case. So what do? Well, you introduce the higher level objects, and then what you want essentially for FLT is that you want to first state these theorems. And then you can reduce the proof to several highly non-trivial statements. And then you can start doing the proof. So I'm going to talk a little bit about Lean. You know what Lean is about. So Lean 4 is a programming language and the proof assistant. You have dependent type theory constructions. If you know Coq or Rope, we have the same basic type theory. Each element has a type. It's type P. For example, the rational number 0 has type NAT, and the rational number has type Q. Types also have types, and has also type. You have, like a hierarchy. Probes at the bottom, and you start playing the bottom of infinite chains. Propositions correspond to elements of probe, where verified proof for proposition P corresponds to an element P of P. Right. So this is. Okay, so the commands, definitions, and abbreviations are the same thing. You use them to define objects. What is a definition has an identifier foo, it has a type alpha, and the bar, which is the term. Here's an example. You want to define this engine called double. Well, it's x of type n, and then you have x plus x. That's a proof. And then we can move on items. So Lean commands a theorem. When you have a theorem, you have an identifier C. You have the type alpha. But the difference is, I'm Greek, sorry, A. But the difference is that big A has type prop. Okay, so A is a proposition here, and that's a theorem. Implies UV plus B. And that's the proof. You have the soy identifier, which is a command that produces proof of anything, provides object of any data type. So, what about MathLib? So we have Lean has a communication mathematics library, has a lot of covers a lot of undergraduate and MSc material on like a lot of areas. You have it's community driven. You have a lot of professional mathematicians who know the material for FLT and also the maths. And then you have this philosophy that says that the formalized work has been done in the maximal generality and not in an ad hoc way. So you can use this material for in as many applications as possible. Large-scale formalizations are difficult to achieve. It's estimated it will take a very long time to have a complete formalization of FLT, and you need a lot of different. You need a lot of specialists in different fields of maths, and that's the only way. You need the library. You don't want fragmented libraries. You need like a comprehensive library in order to ensure continuous maintenance of the code and having everything at hand. What happens with projects that new material is initially not ready for use inside the project because you might change it a lot of time, and you also need to build on top of the library. And in the end, it turns out that you actually have to rewrite things again and generalize them if you want them to become part of the library. So that's what happened with the liquid tensor experiment, actually, with the perfect fluid spacer. Because you have a lot of code that is not mature enough, so you cannot enter the library. So you have like some really cool math that is not there. Okay, so more NPS. What do? Well, you want to write the proof from top down, and you use this SORI identifier to fill in the subproofs. You obtain this proof sketch, this roadmap, and the proof will be built incrementally. You start doing all the proofs, and then you can see what is missing, and from the library what you need to formalize in general, and then this keeps the maintenance of the code to bare minimum. And then you can start developing the library in parallel because you can have continuous maintenance, of course, but then you have accessibility, usability of the code. And you can have a blueprint and you can divide the work, and you can see what kind of potential signs or issues come up. Okay, so there's a strategy, let's say, or some kind of like a hierarchy or whatever of what you can start doing. So there's a lattice of 7 possibilities. First, the proof the theorem as well as the math version. So you prove whatever you want to prove in the maximal generality from the beginning. You start like that. You can be level 2, which is you formalize the theorem with all the definitions involved, including all the proofs. But this is going to be in an ad hoc way, just for what you want. Then you have the third level is about only the statement, and then you have like some other options. You can have the statement fully formalized and all definitions involved, but props may be omitted everywhere. So you sorry theorems, not definitions. You don't sorry data. You can formalize the statement, but with definitions that are sorry free, but sometimes hacking so you can avoid working with these difficult proof obligations, right? So, but what you have to do in this case is that once you want to go on a higher level, you have to prove that this is, you can either redefine everything or you have to prove that these definitions are equivalent to the usual definition. Okay. So, or you can have a combination for it. So you can have unorthodox definitions and the usual definitions. And number 5, I suppose you sorry everything, both data and theorems. So the interpretation of 4a, 4b, and 4c, okay, here's the lattice. We can say def, give an identifier, give it a type. We're not allowed to say def, given an identifier, given a type, sorry, if A is a type, but we're allowed to say theorem T of type P is sorry if P is a prop. Formalize FLT. It's going to be very challenging to achieve a complete formalization of many of the higher power theorems with FLT. And even formalize the statements, you can see, is already an issue. And you need a lot of time and probably decades. So we're going to be in situations where the first level, second level, third level are not feasible. So we have these variants as our only option, just for the statements, of course. And for the Deligne theorem, the situation is similar because will also take a long time to formalize. And our approach was to work on 4C level partial formalization. So we can sorry propositions, we can sorry theorems, but not definitions. Definitions can be stated though in general ad hoc or unorthodox ways. So, and we have defined all the mathematical objects in the statement of the Deligne theorem. So I'm going to start going through these objects. So we have the classical theory of modular forms in mathlib, and among the most important modular forms that are called eigenforms. And here's just a snippet of how this looks like. So we have a modular form, and it's an eigenform if it's satisfies its properties here. Okay.
Can you read the code for us in understandable language?
So you have what you have here. You have 2 natural numbers n and k. You have a modular form. Common. This is a group, and then you have this is a character. This is another map. And then you want this modular form to be non-zero, and for all q, which is a prime, and q doesn't divide n, there exists a complex number, such that for all complex numbers in the upper half plane, there's this thing that is called the Hecke variable, which I haven't shown, that is equal to alpha times the modular form applied to z.
And is there any explanation of what this thing is useful for?
Well, it's the simultaneous eigenvector for this. So essentially, this is just you're going to have an eigenvalue. So it's going to be an operator, and then you have like so this is like tz equals alpha f of z.
You could. The only reason you have the z over there is because you have a restriction on the domain, right? Because what you're saying is that like the form is an eigenvalue of something.
There's no restriction on the domain. That is the domain of the.
Well, then why do you have this irreducible thing here?
It's not irreducible, right?
For every z in the upper half plane, blah 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 blah, like z equal Because
No, this is.
don't you have extensionality?
Well, or are you saying like heck operator equals lambda z?
The heck operator of FH.
This is the argument
Chi.
that it's here.
Yes, you could omit the z on both terms.
No.
And remove
A times f of z.
Oh yeah, okay. Well, that's just a times f of
Sure.
z, right?
Yes, you could write this as an equation between functions like that.
It would make the thing clearer, saying like this is an eigenvalue of something else.
Okay.
Eigenvector.
Yeah. Next one.
Wait.
What's a heck operator?
Yeah, so are you going to explain these things or are you?
No, that's the
going?
point. Like, I don't want to get into the maths.
Not even.
Just say 4D or something like this.
4D.
Explain nothing.
Or the-
Sorry, any explanations?
Explanations are all sorry.
But like, is there, for example, some intuition behind the heck operator?
Yeah, this is this is just an operator. So this is essentially, if you want to see it different, it's like T Z equals alpha Z. Okay, so alpha is just an eigenvalue.
But like, why is this heck operator important, or like, what does it do, or is that what you just said, or?
Is it another modular form?
No. This is just we need to get into the maths.
I think that's exactly what the question is.
Well,
The question is, could you get into the maths, please?
but like very, in a very high level way, right? Like you have here audience of people who know very little about this, so.
Yeah,
can
that's right. That's the thing. I just want to show the code, like what.
I mean, if you jump to the code, then we'll have go to definition, right?
Actually, so I actually want to know, like, so I know mathematically, like that condition should be formulated as like you like add the heck operator onto a modular form, and it's just like a eigenvalue or something. So
Yeah.
why would that heck operator function takes in like so many like parameters?
Well, it takes like so. Okay, so that's don't want to get into the maths because we define this in an ad hoc way. So what we did was like this is a modular form, in fact. Okay, and what we did, we defined it as a sum, as a complex sum of stuff, right? What we didn't do is we didn't prove that it is a modular form. So essentially, this is just a sum of stuff, right? Because that's why I want you to see this as a complex sum, as a power series.
So that's why you are not using that's why there's an,
Yeah, it wouldn't have the right type.
Yeah.
And it also I mean, if you think of it as a function producing modular form, it only really takes f and chi and it produces another modular form. It takes two more arguments, h and hqn, which are just saying that these things are well typed, or h says that q is a prime. HQN says that q doesn't divide n. They're not very interesting assumptions.
oh, they are what's needed to prove or to ensure it's a more.
To make sure that it makes sense.
Okay.
And then z is just applying the modular.
Yeah. Galois representations. So what's a representation? Well, let's say you have an exotic group, okay, and you want to study it. What you do? Well, you map it to a group of matrices because we know groups of matrices very well, and that's the idea here. And then here you need a two-dimensional Galois representation. What is here? So case topological ring. So it's a continuous group homomorphism. So you have this exotic group, which is called the absolute Galois group of the Hessians. And then you have the 2x2 matrices. And then you just map it there.
Is a Galois representation just a representation of the Galois group, or is there more conditions?
Yeah, you can do whatever you want. Like, yeah, you can map it to it. There are a lot of examples. So here we only have we can only actually have the type. It's continuous monotone. You have the Q-bar, the algebraic closure, and actually this is a Galois group essentially. This is this. And then you have this, which is closer to infinite. Yeah, so that's the second object. And then we have what it's called the Frobenius element, which is essentially an element of the Galois group. So the Galois group is the group of automorphisms from Q bar to Q bar and fixing Q. And so essentially it's an automorphism. That's the definition.
Non-computable.
Yeah, it's non-computable because we're using axiom of choice.
It's not a line. This wouldn't compile.
Would you go a step through the thing? You're showing code, you have to read it.
Okay, so we have field K and L. K is a number field. We have an algebra here of L. It's Galois. You have a valuation subring. This is just it's a subring in L. So it's not the full field. It's not the top field. And you have this decomposition subgroup, which I haven't talked about. Have talked about, which is basically a stabilizer of this Galois group acting on these valuation subrings. And then what you have is what's that? Oh, okay. So this is you have some stuff that's called the residue field of these. Right, so what you do is you jump from, you take the residue field of the valuation subring of the top field over the residue field of the valuation subring of the bottom field, and then the valuation subring, the residue field of the valuation subring of the bottom field, K is finite, so that's why you have this fin type stuff, because that's theory, and then you basically have this subjectivity map, and what you can show is that this decomposition subgroup is basically isomorphic to the Galois group. So what you do is you pull this element back. So you take this pretty of the special type of automorphism in this group, and then that's the Frobenius element.
I have a lean loop question.
Yeah.
What is let I? And why does it get?
You introduce it's like an auxiliary instant, right?
Yeah, but there's there's let F. I get that you're introducing something which is called F, has a particular type, but
Yes.
let I.
Well, this is just an instance, right? So when you try to, where are we? If you try to define this thing here, right? The moment you write this thing here, then you're gonna ask, Lin will be asking for this thing to be finite or thing type. So you just introduce this instance in there. I could put it like outside.
No, I mean there's no name. You just put it in a context and Lean finds it.
Yeah, it's just an instance because you don't need to names and instances. It's the type of
In order for some of the types to type check, it needs to know, if you define, I don't know, what would it be in this case, like the residue field or something is going to ask that is defined for a finite type. And so there's an instance which is like fin type, and it says fin type, it's saying that this is a finite type.
An interface.
It's similar to like when you ask for a group structure or ring structure or whatever, you can do that for fin type as well. And here, there is no global instance saying that V is a fin type, but it's derivable from the facts and context here, and what he's doing is producing proof of that. I think writing the types of things might have helped with making this a little bit clearer.
Yeah, and we use axiom of choice. to pick this random element. I mean, the spatial type element. Right, so that's the formalization of the full statement. And now I've added comments, so you don't have to ask me what everything means. You don't have to parse everything. Yeah.
So when you use the axiom of choice, that implies that there can be multiple elements like this?
No, actually, it's only one here because this group is cyclic, so it's generic. It's just unique element.
Couldn't you just, why do you have the axiom of choice then?
Because it's an ad hoc definition.
You're saying like, could this be done without the axiom of choice if you had the proper definitions?
You can, okay, so you see this here?
Mm-hmm.
This is like a map. The map from the composition group, the decomposition group is a subgroup of TQ, okay? So there is a map between them, same way. And this map is surjective. It's injective, but it's also surjective.
Wait,
But
what?
the group,
There's a map from the composition group to the whole Galois
yeah,
group?
because the kernel of that map, when the kernel of that map is trivial, you get this, you get injectivity, and then you have to prove that it's surjective. Yeah. So this is, but this is a very tricky theorem, and we omitted the proof of that because
Okay.
If it were proved constructively as like a sigma of an element such that it maps to this, then you could just pull out the first component of that and use that instead of choose.
It's interesting that you're like, not having the proof of the thing leads you to need the axiom of choice. I mean, it makes sense in a sense, but
Well, having the type stated as there exists a thing, using surjectivity of a function. Surjective is defined as for all A in the target, there exists a value of the source such that it maps to it. If you wrote instead for all A in the target, sigma of something in the source such that it maps to it, then you would be able to just extract it here. So it's a difference in the type of this intermediate theorem that's been sorted. And then depending on how that's proved, it either may actually need to be and exists, or it might be a sigma.
Back to the theorem.
Oh, but like, do you have a plan? Like, do you plan to prove it classically or constructively or whatever that exists?
Don't ask me, ask him. I don't even know.
Back to the slides.
So,
Should I go back to the slides where I was saying all proofs are classical?
should you, but are you going to prove it? That's
Okay, so you need okay, so if I remove this and I try to print the axioms of these definitions, of course I'm gonna have somewhere the fact that you're always gonna have like the axiom of choice somewhere because I'm using lean, right? Which is a
I'm
classical.
not talking about this stuff, talking about the whole thing.
Oh, the whole thing constructively.
No, just prove it, just because I know it's just a statement. How hard would it be to prove it compared to stating it?
Well, I mean, if you ask Kevin, he'll say 10, 15 years.
Oh, wow.
That's because you're missing the math right now.
Holy shit.
Sorry, I thought you were asking about Fubini's. I was like, okay. Cool. Okay. Yeah. Can you
I mean,
parse it?
how big is the proof?
I don't know, but it's also a generalization, right? It's not just cycling anymore. It's not just a special case at one.
Right. But like, how big is the proof on paper?
I don't know. The paper, I don't think the paper is really long, but the references is the problem, and the references are like a lot.
I have difficulty conceiving of theorems that would take longer than a year to prove. I have difficulty conceiving of a theorem that would take longer than a year. Yeah.
I mean,
If you get all the people who know what they're talking about in a room, they have to work together.
well, if everyone works together.
Yeah. Assuming that there
nice
aren't
each other, then-
other organizational issues, like formalization-wise, I don't know anything in math that would. Classification of finite simple groups, most of the work is actually figuring out what the heck the proof is. once you know what the proof is and you're actually like,
Yeah, but that's the point, right?
yeah.
When you start digging through all of the details, things just grow exponentially. I think that's the problem.
Or you don't have someone who knows the material with you or, you know, accessible in some way. Like here.
No, like Kevin, that's what I meant.
Yeah. Kevin being involved in FLT is a major factor in this being able to happen, right? If you didn't have Kevin, you know, who knows Taylor and worked under Wiles, you know, having someone like that involved in the project is a huge improvement on.
So you need specialists.
Yeah.
Of course, you need someone who knows the proof, but also you need a lot of people from different fields. And there are even like branches of maths that people don't really care about computers. It's kind of trying to get them involved.
So you said FLT is estimated to be 350 person years, and this building.
No, 350 years of mathematical knowledge that needs to be encoded. Now it might be 349. So, yeah.
Although you mean like centuries?
Like the actual, yeah.
Going back to 1637 or
The volume of knowledge.
When it was stated, right?
So do you or Kevin have passenger estimates on FLT and what they?
Last time I talked about this, I just imitate Kevin and asked for 100 million pounds. So I could, yeah, that's the idea, that's the rumor.
How long did you take to write this?
In the beginning, when I started my first year, I mean, I was also learning the system, so it took me longer. But like maybe it was like 9 months or something.
9 months. How is this? Have you any idea how this stating this compares to stating Fermat's theorem or?
You mean the other, the high-powered theorems? You mean?
Yeah, I mean in terms of work.
I don't know. I mean, if you have a lot of people working on this stuff, like, you know, how long did it the tensor experiments? Like 2 years.
Also probably worth noting that writing out the definitions is the part that really can't be parallelized as much. Once those are in place, you can sort of
Prove
hang
them.
on.
Okay.
Instructions are also going to be difficult.
And is there an estimate in the number of textbooks or chapters that need to be formalized to get this?
Is this
Statement?
is this in textbooks? Are there textbooks that cover this proof, or is this research papers only?
I think it's mostly it's done in Kevin's guidance. So there were like a lot of experiments. So, like this definition with Rubin, we have to change it like a couple of times.
No, I mean Deline's theorem.
This thing.
So, like the actual theorem in mathematics. Like, is it in textbooks? Can I pick up a graduate textbook on number theory stuff and
I think
Deline's
it might
theorem?
be a few, yeah. The thing is, like, the material is like spread out. It's not really like, it's not gonna get a book saying, okay, this is the links.
Is it something that like research mathematicians think is well known to, you know, everyone?
Yeah, so I was writing a paper about this and asking why did you write this in the blog? He's like, well, because I think it's important, and I was angry that all these AITP people think they're going to auto-formalize. So this is like a very, apparently he thinks it's important and it has to be in monthly because it's a big thing in algebraic number theory, like research level number theory. And theoretically, yeah, if you have all this material, then you can start stating stuff from the language program or whatever.
Do you know when it was proved?
Hmm?
Do you know when it was proved?
I think that was like, I think it was the 1974 or something.
Oh wait, so what's the statement?
Where is the statement?
The statement was.
Wait, you want the whole thing? Okay, the statement is the.
Is this the statement?
How do you explain what this is when you use normal person words?
Oh, that was a normal person definition in the beginning. Oh,
Okay.
statement. Right?
Yeah.
You want a statement, okay. That's fine.
That's not a normal person words. Statement, nothing is like.
Did we get it statement?
Yeah.
Oh,
Yes.
this one. Yeah, okay. Okay. So can we recognize these words in the formal version?
Well, you have this probe. You have this eigenform, and you guys are asking about the Fleck operator. So that's in there.
Is the x squared
The
minus a?
scalar representation was this map that I showed you. Yeah, this Q not defined NP and prime, blah, 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 it was there.
You have a form with a type, you have a character for that form. Some conditions on the types.
Oh, you have a reference here. Do you know how big the reference is?
Oh, the references.
Yeah. Well, no, just that one. The one that you preferred, number 3, whatever it is.
Oh yeah, you want to go
Do you know how big is it?
I can check. I think yeah, that was the original paper.
But how big is it? Like 10, 50 pages? How?
I think the reference that I used was just to get the statement. I don't remember if it had the proof or not. That's the thing.
But how long was it?
30, I don't know, 30 pages maybe.
Okay.
But the reference is the issue.
Did you have like to go into recursive mode?
No. So the idea was like, okay, we have these definitions.
Mm-hmm.
We have these objects. Let's just define them.
Okay.
That was the idea. We didn't get into.
And that's
so,
always
this-
a reference.
Yeah, we just you just random like different books or whatever.
Okay.
So it wasn't really getting the proofs. Then you need the references, and you also probably you need the shortcuts or whatever. So you need an expert.
Mm-hmm.
But this is something that you find in textbooks? Like, is it?
Well, if you get the original papers from the 70s.
Well, I mean, if there's an original paper in the 70s, but then in the years since then, people have, refined the proof and like understood it better, and now it shows up in 100 textbooks, then, maybe you could just pull one off the shelf and start working. Right?
I think it will. I think it's one of these big theorems that it will require discussions with Deligne, maybe. Like you have FLT with Taylor. So I don't know.
So after stating it formally, how well would you say you understand the thing? Like how stating it formally has it made you understand the thing better?
I mean, what Shelby understood was like just reading and learning these definitions.
Where did you get all the definitions? Did you like read? Did you?
Yeah, just like
There's some.
they were like reference. I mean, they were just like books.
Wikipedia.
Wikipedia, it's actually useful.
Very useful.
And also for defining these things, also Zulip, of course.
How confident are you that the definitions you wrote down are all right?
Are all correct?
Yeah.
Well, it passes some sanity checks, so I guess they're fine.
Define sanity checks.
Oh, Kevin looked at it.
Oh, okay. And it compiles, I guess.
It compiles, yes. It does compile. Yeah, and
Files and in Kevin's.
Yeah. What
You know that there
which
exists a
makes you
prime?
more confident?
we actually defined this prime.
Right.
So it's it's a prime with some conditions.
Does there exist one?
There exists a prime because of the theorem. with some conditions.
Constructive?
And it's really funny because when I first wrote it was like define P and then gave a type.
But is it like,
Actually, it should be Q, not P.
is the proof of existence constructive of the prime?
The proof? No. Because it comes from a theorem, and the theorem is an existence theorem.
Okay.
So you just pick a prime with this proof.
Oh, I mean, but for a particular modular eigenform, can you compute
No, this Q doesn't come from there. It comes from a theorem of, which is a number theory, like within.
okay.
Yeah.
Cursed.
About 15 more minutes of questions.
Show us the code.
So you were showing us the code and
Okay, you want to go?
somebody
back?
asked you to explain the code.
It was you.
No, I think it was you.
But also, I have the question, so let me phrase it very bluntly. Actually, how much hope do you have for actually that it is the right unorthodox formalization? You stated it unorthodox, you called it unorthodox in the beginning.
No, it's unorthodox. I mean, so when some of the material is finally formalized and it's in mathlib, then we can either use that material to replace it, or we can just keep the same definitions and then that's prove that they're equivalent to the definitions in mathlib.
So you say the most value out of it is that mathlib will be enriched.
I mean, for FLT in general, yes, and also from
It
this
will
project.
be, but you are not sure whether Deligne's theorem will be.
In order to be accepted into mathlib, it has to be general, right? It has to be generalized.
Yeah.
And these are all stuff that is underway. So it's just for sociological reasons, as people working on different kind of things, and it takes time. But you just want to build the most usable blueprint, and then that fits well with other people's work. So always, look at what other people have done and then just make sure that you require like minimum amount of work to complete this. Sometimes they're real time. Sometimes we'll be like, we need this. Someone in Zulu would say, okay, here, here it is.
Will there be a vote on whether this is the correct formal proof sketch? Or is it just Kevin?
Well,
Or-
That's a vote.
Yeah.
Very limited constituency.
Yeah.
So this is not the proof sketch, right? This is just the theorem.
This is
The
the theorem.
statement.
Well, there's a
The
proof
statement,
sketch
yeah.
over there.
You mean the sorry?
Yeah,
Well,
okay, yeah, that's true.
that's a very special proof sketch.
But
It kind of puts into question a bit the whole ethos of formally proving things. It's like understanding the statement requires a PhD, you know?
No, that's not unusual.
Yeah,
For
I
statements
know.
to be in many.
I know, but the thing is, like, okay, the system is ensuring, not in this case, but anyway, if it's complete, that like, okay, this stated thing is correct, but it tells me absolutely nothing, you know?
But it tells you more than nothing, because like you can click on these things and you can find the definition of it. So, you know, now that he's formalized the statement, you can, this is essentially another means, like, you know, you can pull up a math book and then it says, oh, you know, this is an unramified form, and you're like, what's an unramified form? And then, you know, doesn't work because it's paper. But here you can find out what that means, right? You can, so this becomes more searchable. It's, you know,
I'm
this
slowly
is,
becoming more and more convinced of Michael's arguments.
yeah, no, this is one step on flexi formalization, right? This is,
Well,
And I would say that actually correctness of the thing is, it's not the primary point of this, right? This definition, this statement is almost certainly wrong, I'm sorry, but like, because it's too big, right? There aren't enough, you can do some tests, but there's no way you can do enough tests for this. The actual test is the theorem. So once you start proving the theorem, you're going to find a half dozen minor mistakes that were made in the process of this. You fix them, they're probably going to be minor, not causing problems, and then you'll have the right statement
You
in the
probably
process of
know
writing.
more about the theorem then, right? In a sense.
Oh, yeah, well, I mean, certainly you'd learn a lot more about what this statement means in the process of proving it.
But I would say this is a personal position, I guess. I don't have much to support it, but when I see things like this, it is my intuition that we need more abstraction. Like this is not being stated at the correct level because there are too many moving parts. We need to abstract things away in order to be able to state this in a more reasonable fashion. It's more a problem with the mathematics than with the code, in a sense.
But there are things in mathematics that are inherently extremely complex. And we are kind of in an interesting point to be at where we have these projects in mathematics where we're hitting the one brain barrier, or even the this can be done in a small group barrier, and without computers that is actually unsurmountable, right? And we know, for the computer scientists in the room, this paper about the mythical man-month paper, which is really that if you have these big computer science projects, adding people to the implementation team actually makes the deadlines further away, because you kind of hit this communication barrier where things get more difficult and less likely to succeed. And in computer science, and IT, we know there are problems which without a completely fresh take we cannot do. And that's where essentially this mythical man-month paper was the start of software engineering, essentially. That's kind of made the possible projects bigger. And I see the main value of formalized mathematics not so much in the 1 or 0.001 bit of information they glean, but they actually make the projects we can do in math bigger, if we can tame the de Bruijn factor, essentially, right? How much longer does it take to formalize something than do it with pen and paper? And
How much
some
longer
of these big projects
need to do it compared to Deligne doing it?
yeah, whatever. I mean, there's a lot to be filled out in this argument, but I do believe that eventually those things will make the projects we can undertake in math bigger, because it's not one brain that is needed, or 7 brains, which is typically, but they run into problems as well. We can do the bookkeeping on the computers, right? We have with the classification of the simple finite groups, right? We have some people who believe that there is a theorem. Unfortunately, it's a paperscape of about 200-300 papers, which some people believe fit together, and some people try to write them down in a coherent manner, and they have basically stalled at 6,000 pages of proof right now, and they believe they would need something like another 5,000 pages of proof to just write it up coherently.
That, to me, points to the fact that we don't really understand the subject. That, like, when you start analyzing objects, we live in an era of mathematics where we do everything by analysis. We never synthesize things, and that's a problem because complexity only increases. Sometimes you need to like cut down complexity, define clear interfaces. It's about modularity. I think I agree with what you're saying, but only because programming the thing forces you to reorganize the subject, to understand better
But
what's
certain things are complex, and there's no way of actually cutting them down.
We have 4 minutes left. Are there 4 minutes left to your talk? Because this sounds like a coffee break.
I think he's done.
Yeah, we can apply the same process to obtain partial formalizations.
What are your?
In the same way. What? This?
I also want to see.
Okay. Yeah, we can build upon this work that's really complete formalization of Deline's theorem. Same way we do for FLT. And
Do you know who one is?
sorry?
One can now build on this work.
You want a constructive one, right?
Or constructed many.
May I ask a completely different question, not in the direction of Michael, but to everybody? For the organization, I've been a bit worried when I came in mornings to this beautiful villa, is that I had trouble finding out who or if anybody is there. Well, if is easy. Nicolas is always here at 8, at least, and then, but of the others, I don't know. And there are some people of you I haven't talked to. And so I also had the feeling that many of you didn't really have an expectation of who they meet here by serendipity. And I think meeting and talking to people here is something which we should cultivate, and we've tried to cultivate it. And these talks are something which actually seem to work. There's 3n plus k people for non-trivial n and k in the room. This is good. We'll be talking over coffee. But this is rather late in the day. And I was wondering whether it would be a good idea.
Well, the talking lasted longer than the talk, so.
And whether it would be a good thing that we kind of meet here at 10 for some value of 10 in the mornings and basically tell each other what we've been doing. The usual high-low or what I would like to be doing or whatever, anything like that.
I've been doing some things,
Yeah.
and I would, like you're saying about the talks, I don't have anything that takes more than 5 minutes to explain, so I couldn't, do a talk, but I wanted to.
When I have this kind of a talk, it usually takes 2 hours, but my 5-minute talks. But yes, but I think not like talks, right? More like this is what I want to do, and I've been completely frustrated because the sigma wouldn't become small or whatever.
And I would need help with lean or C.
Exactly, and so that we actually have the expectation of meeting in the morning, and then afterwards we know people are here, or I've seen Natalia already, so I know where her office is and I can just go there. Otherwise, I have no expectations. And so is this and it's not for control, obviously. Who would we be to do
Maybe
that?
what we could do is, especially for the newly arrived people, not to give like a 1 hour talk like this, but give like a 5-10 minute pitch talk. Here's what I would like to.
Yes, those kind of things. So I would like you to think about this, and maybe then we can do something.
I think people in agile project management call this the daily, so we could do a daily.
One thing and sort of mitigate this with a little bit is that I do also want to make sure that we have time to actually like spend time working, uninterrupted on some task. And I don't want to just like break up everything with meetings and then like we talk and then we don't actually do anything.
So meet at 8.
Mean that?
Well, like maybe not doing it every day, for instance.
Or we just do it like right before lunch. So people are gonna be going to lunch anyway, and then.
But it could be just one day.
That's a great
Like,
way of
typically
making meetings
people
last.
arrive on Monday, right? So I don't know, like, let's say Monday it takes to settle up here and see the people, and then Tuesday or Wednesday could be some sort of pitch talk meeting once in a week where people say, well, this is what I would like to get some collaboration on or discuss with people, etc.
Yeah, but I tend not to understand what people are talking about on Mondays. But if it's repeated on Tuesday and Thursday, I can actually understand a little bit more.
Before lunch could be good, right?
Yeah, I
It's a way
also like
to
the
keep
lunch
it short.
idea. I think it's
But
a
then
good
there's
idea.
lot, then there's, I would just, then there's not a lot of time to interact before the talk.
Lunch.
There is
There's lunch.
Right, so I like this, like, we talk about the thing, the people who like it go to lunch together, and then find out more about the thing.
Okay.
Plans.
Like the way I do it in Prague is that we discuss things over the lunch, right? Like, but it's like with 10 people that I know, right? And so here having like 15 minutes before the lunch for the shy people or the non-eating people or might work, right? Like it's like.
Okay, let's talk about this over coffee.
No, wait.
Okay.